Welcome to my talk on optimal weak to strong learning. My name is Martin Ritzert and this is joint work with Caspar Green-Larsen. In the field of learning, we are interested in hypotheses that generalize well on unseen data. And a learning algorithm is then an algorithm that can produce such hypotheses. We say that a learning algorithm is a strong learner if, given enough training samples, it returns a hypothesis that achieves an error of at most epsilon on unseen data. So this is what we want. But sometimes we are only given a weak learner, that is, a learner that produces hypotheses that are just slightly better than chance. And we say it is a gamma weak learner if the expected error on unseen data is 1/2 minus gamma. Well, such a weak learner is actually pretty strong. We know that there is an algorithm, namely AdaBoost, that uses many weak learners and combines them in an ensemble method, so combines them via majority voting to become a strong learner, to achieve any desired epsilon. Well, the key question when turning a weak learner into a strong learner is then, how much training samples do we need? And this is the question we are also addressing in this work. So how many samples, m of epsilon and delta, do we need to achieve those two bounds, epsilon and delta? Yeah, and this question was addressed before, so there is a previous bound for AdaBoost, and this just says that the number of training samples that we need depends in this manner, and it depends on the VC dimension of the weak learner, on the advantage of the weak learner, of course on the desired accuracy, and it also has this right hand side term that accounts for untypical training data sets. So we improved upon this bound, and our new upper bound is essentially the same, but we were able to remove those two log factors. And not only that, we proved a matching lower bound. And since those two bounds match up to constant factors, we know that we make optimal use of our training data. So our algorithm, which I will present next, is optimal. And how does this algorithm look like? It essentially is a very simple algorithm. It starts by taking our training data and enumerates largely overlapping subsamples of this training data, following a procedure introduced by Steve Haneke in 2016 on his work on optimal PAC learning. We then run AdaBoost on each of those subsamples, creating voting classifiers with a large margin. And finally, we return the majority vote of all those classifiers we just obtained. This means that the final classifier is a majority of majorities because we take a majority over something that is returned by AdaBoost, namely something that's also already a majority vote. So what did we show in this work? What did we prove? We gave a new weak to strong learner that removes two log factors from the best known bound. And we came up with a matching lower bound, such that together we have optimal sample complexity. While proving the bound on the strong learner on our new algorithm, we also came up with a new generalization bound for large margin voting classifiers in the constant error case. So what is still left open? Well, the question of this double majority. Do we really need it, or is there a twist to AdaBoost that allows us to use a single majority and still have optimal use of our training data? And a more practical question is there a way to reduce the number and size of calls to AdaBoost? Because at the moment, this number is relatively large. Thank you for listening.